Here we go. Hello, everybody. Welcome back. Hope everyone's suitably caffeinated. I've got great news. The lunch has arrived. So it's only one small presentation from George before we can have lunch. Just a quick reminder for everybody who's here. We are doing a hackathon tomorrow. Same location here from 10 o'clock, I think, till as long as we last, of OpenZFS hacking. So in light of that, we kind of wanted to generate some ideas outside, from inside the room, really. So we've got a free T-shirt to give away, which is modelled by my able assistant. Yeah, I think we need a collective ooh. Ooh. Okay. So we're going to give that out to the best hackathon idea. So, raise your hands. I'll throw you the mic, and you can come up with the best hackathon idea. It can be super complicated. It can be one I've already nominated you for, whether you like it or not, or anything like that. So, floor's open.
You must be a medium to.
I have other sizes tomorrow.
Anyone? I mean, I don't have to go through names because I can name quite a few people here, so we can go one by one and force people. Fine.
How about one idea?
Yeah. Okay. One idea. Anyone who for a hackathon, something that they kind of a feature for ZFS, an improvement to ZFS. All right, Sasso, you've nominated yourself for BP Rewrite tomorrow, so congratulations. And in fairness, Andrew Stallman on the way over did say it didn't seem like that BP Rewrite was going to be too hard. So he's nominated himself to help Sasso on that. So anyone at all?
Multi-modifier protection.
Say again. Multi-modifier protection.
Supporting for clusters so that you don't accidentally import a tool that's shared between two nodes.
Okay, well I'm going to give Dan the mic, and then he can re-explain that for everybody.
So the idea is that in some clustered environments, you have multiple nodes that are able to access the same disks. What we need to do is to make ZFS aware of that shared space, so that you don't. We're going to be able to prevent importing that pool on both nodes in the same time, corrupting data.
That's an excellent idea. Congratulations. And is a suitable medium as well. Okay, moving on. So let's.
If you come to the hackathon tomorrow, the first dozen people who show up, we'll get you. The first dozen people who come to the hackathon tomorrow, I have more T-shirts for you.
Cool. So hopefully we'll see you all tomorrow, same location, but from 10 o'clock. Okay, so moving on, we've got George, so doing a performance retrospective from Delphic. So over to you.
Thanks. Thanks, Ryan. So, out of curiosity, how many people have really dug into ZFS performance?
How many people have run into ZFS performance problems?
Yeah. So the question was, how many people ran into performance problems? Okay.
Yeah.
Okay. Cool. So, what I want to go through is kind of, and this is going to be, since this is a community forum, this is going to be a community presentation. So I expect a lot of participation. So we're all going to, for the next however long, kind of start looking at a performance problem and figure out and kind of come up with proposed solutions. So we'll look at how pool performance can be impacted, what is out there today, what are things that we've already done, and how they improve things, and then we'll take a closer look at performance problems and kind of talk a little bit about this thing that Matt mentioned, which was the allocation throttle. So let's start. Everybody get excited. We're going to start looking at a performance problem, or maybe there isn't a performance problem. So if somebody came to you with this type of, and this is actually a real system, came to you with this type of information, what things could you glean from this that would either tell you it's good or bad?
So I'm here to run for with the mics. So anyone?
Okay, so for example, what do we see here? We have a system that looks like it still has quite a bit of space available. How many people run their systems to this capacity at 71%? How do they perform? Depends, right? So sometimes good, sometimes bad. But we do have quite a bit of space, and we also can kind of take a look and see that like fragmentation doesn't look too bad. So we kind of, at first glance, look at this and say, okay, maybe this pool will actually perform well. What if we get a closer look at it? What do we see here? So as we start looking at this pool, now we're looking at each of the individual devices that make up this pool, and what are things that we notice? So it looks like there's been devices that have been added. So some devices have more free space than others. It's true. Some devices are bigger than others. So this is actually a very common thing that we see with our customer base. How many people configure the system correctly the very first time, every time? Okay, there's at least 4 of you. Okay, well, unfortunately, not all our customers do that. Most often what you see is you create a pool, you start off with some configuration, and then later you decide to change your mind. Primarily you change your mind because you need more space. Or maybe you can't buy that drive anymore, so you get something larger. Well, so in this case, we have quite a number of disks that are actually twice as big as the original ones that were first added. We also see that there's a bunch of devices that are over the 80% threshold. And those that have been using ZFS for quite some time, 80% has been a number that has been out there for quite some time as like the known cliff of performance problems. Oftentimes, you don't get to 80%. To get to 80%, you might be lucky. I'll tell you that this particular system has actually run close to 90% at times. Barely run at times. And we also have kind of a big disparity on free space. So we're not expecting this pool to perform great. If we had our chance to do this over, yeah, we probably would start from scratch, create all new devices at the same time, same sizes, and maybe ZFS send, receive it, all the data over. Fortunately, we don't have that luxury. So what are things that we observed with that particular pool? The thing that when we started looking at this, and this has kind of been an ongoing performance investigation for us, we see this not only in an internal system, which this happens to be, but also our customer base, which goes through these scenarios quite frequently. So we notice that as devices start to get full, they take a lot longer to allocate. Oftentimes that's because they're fragmented, so the actual finding of blocks takes a long time. Use a lot of CPU to do that. Now writes that we would intend for them to be like sequential turn out to be a bunch of random writes because the free space is scattered all over these devices. So we start seeing performance penalties from fragmentation. We start seeing metaslabs. How many people are familiar with metaslabs? Okay, a few of you. For just a quick synopsis of metaslabs so that everybody understands. Metaslabs, you can think of them as regions on a disk. So the way that ZFS does allocations is it takes an individual device and carves it up into approximately 200 equally sized regions we refer to as metaslabs.
Why 200?
Question is, why 200? Because 100 didn't seem right and 300 seemed like too much. The reality is 200 is a number that has existed from the beginning of the ZFS days, I started in 2005, and so it's been around since then. Nobody knows. There are now tunables to actually change it because we are finding that different configurations perform better either with more metaslabs or fewer. But yeah, it's one of those mysteries of life. But anyway, when you have these different regions, in order for you to be able to allocate from a region, you have to load it first. So you carve up the disk into approximately 200 equal-sized regions, and when you have a lot of fragmentation and devices are full, you're having to load these various regions throughout the disk looking for space. We also found that when you have a configuration like we just saw, where the devices are imbalanced and different sizes, you are not getting the full efficiency of the devices themselves. So we're leaving a lot of performance on the table when we actually start doing writes. And again, we don't recommend people have a lot of imbalanced LUNs, but we have found that in our customer base, and this may be true of system administrators throughout the world, nobody gets the pool right the first time, or maybe the second or third or 20th. We always kind of start adding, and that's the life cycle of ZFS. It's one of the beauties of ZFS. We can actually add devices to an existing system, but we want performance to kind of at least be on par as we do this. Okay, so we listed a bunch of problems. We actually came up with some solutions. So we don't have to solve all those problems during this talk today. We are going to try to solve a couple of them. So I'll do a shameless plug for last Open Developer Summit, where I actually presented on the dynamic Metaslab selection. This was one of the key things that we discovered, and a big improvement on performance when you have these types of pools. Highly fragmented, where you're seeing lots of loading and unloading of Metaslab regions, and when you're actually running low on space. And I'll show you some charts on where we actually, some of the performance gains that we got from that. Those slides, by the way, are available on OpenZFS.org, as well as the videos. So if you want to go back and look at them. However, there are two problems where we have a partial solution that's been around for some time. How many people are aware of ZFS MG no alloc threshold? Couple people. I'll talk a little bit about this and why it's just a partial solution. And then we have another problem that actually doesn't have a solution today. And that is, we just aren't very efficient when it comes to writing and getting full bandwidth when you have configurations such as what we just saw. With regards to ZFS MG no alloc threshold, this is a very coarse-grained switch. The idea behind it is that when you have these pools with big disparities of free space, you can actually set this and say, once a device gets to a certain capacity level, so when it has less than, say, 10% free, stop allocating from it. The idea is switch everything over to devices that have more free space. That way I don't have to pay the penalty of loading and unloading Metaslabs looking for free space on devices that may not have much to begin with. Very coarse grain, and it contributes to this other problem of we leave more write bandwidth on the table.
And write as well. Read as well.
Oh, and read. Yeah, because of the fact that we're having to read to only certain devices. Okay, so let's first talk about the existing solutions that I just mentioned. When we set out to improve write performance, we were looking at making sure that write performance, as you approach the 80% cliff that everybody is so fond of, stayed relatively even. We knew that as we started going beyond 80%, that performance was going to be tough to achieve. So what I'm showing here is random IOPS using this benchmark we call frag. The baseline is the blue line, and we can see this very linear cliff that happens starting at about 60%, and actually, if you were to graph this out, is even starts before 60%. But we wanted to improve on this. And by doing some smarter selection of Metaslab regions, we actually were able to flatten this out to the 80% mark. So you can see here, this is the top line is actually showing us what we were able to achieve using the new algorithms. We still see a drop-off, and as you get to 95%, you're pretty much hopeless. And this is kind of worst-case scenarios. Like I said, we've seen this is using 8K blocks, so your mileage will vary depending on what your record sizes are. But we think there's actually probably even a little bit more room to improve between 80 and 85%, which is an area that we'll probably start investigating, because one of the things that we want to do, and I'm sure everybody wants to do, is be able to advertise that you can use as much of the storage pool as possible. As part of this same solution, we also observed that we can reduce fragmentation using this new algorithm. Again, you see the green line, which is showing us the IOPS curve for the MetaSlab selection logic, and we can see that fragmentation actually stays relatively low compared to the baseline until you get up to the 95% mark. And there's a direct correlation between fragmentation and performance. Once we're completely fragmented, we can't get any IOPS really out of the system at all. So that's what we have today, and that's actually maybe upstreamed. So we think that's upstreamed. We'll verify. Definitely available on the Delphix repo that Matt referenced earlier. But what's next? So now we need to figure out, like, how do we address these remaining problems? Especially since we know that customers are going to continue making the same mistakes over and over, and we want to continue to drive and increase our pool capacities. And it's not practical for everybody to send receive to a brand new pool every, year or two. So first, let's talk a little bit about how we would observe this type of problem. What do you see when this is going on? So just a little background. How many people are familiar with the way that ZFS actually does allocations when you have multiple devices? Few people. So when you actually create a pool, in this case, this is kind of showing like a 3-striped pool. ZFS always does round-robin allocations. So it tries to select, a starting point from one device. It'll go to that device, and from there, it'll allocate kind of a pre-selected amount of space. Once it reaches that threshold, it then says, okay, I can switch to the next device. What that means is that if I start off and allocate 512K from this device, I'll do that 512K allocation. As soon as I reach my threshold, I can now go to the next one, and so forth, and I just keep round-robining across. That means that we can keep everything evenly distributed. We're always doing approximately the same amount, and there's some very obscure logic if you look in the depths of like the MetaSlab code, where if one device happens to be a little bit more, has a little bit more free space than the other, then it tries to give it some fraction above and beyond what the normal limit would be. So that's the way it works. What does that look like when we actually run a system that way? In particular, the system we just showed the zpool list for. So I'm going to go, and you're going to see this update, and I want you guys to kind of observe what happens to the pool, and then we're going to collectively try to figure out what is happening and try to make some sense out of it. So here we are. We're starting off. We're looking in particular at our write bandwidth, because that's what we care about right now. We're writing a bunch of data to this pool. Okay, so we went through several seconds there. What did we see? We'll run it again.
It's kind of like all different amounts to different disks. Especially like the first ones is different than the first half.
Went from very even, quite even, to very uneven.
So went from very quite even to very uneven.
The distribution, the amount of megabytes written per second on each VDEVs
So it appears we're writing more to the more full ones. Yeah, interesting things, right? I mean, like, what does this mean? What is actually happening here? Our algorithm is fundamentally broken. Yes. I mean, why do you think, like, these particular devices that are currently busy right now, why do you think they're the ones that are busy? So, fragmentation, how so?
We want to write the same amount of data and it takes longer because they're fragmented.
So we write the same amount of data. It takes longer to write to these because they're fragmented. Exactly. So if we go back, we write the same amount. We're going to allocate the same amount of data to all these devices. But we have no idea what the characteristics of the devices are when we're doing these allocations. Other than we know that if we try to write to this device and if it's mostly full, it's going to take us longer to do the allocation part, which is finding the free space. But it's also going to take us longer to actually write that free space, write those blocks once we've done the allocation. Because it might write a little bit here and a little bit down here, and we're seeking all over the place. So we pay the penalty twice. We pay the penalty of trying to find free space. We pay the penalty of actually trying to get this on disk to stable storage. And that's exactly what we see here. When we start running, everybody's got about the same number of allocations. Then all of a sudden, some devices start going to the point where they're not busy at all, and the ones that remain are the ones that tend to either be most full or most fragmented. So we end up with these devices that are sitting there, and we're not utilizing the bandwidth of them during the entire cycle of our writes.
And those are the fastest devices.
And those happen to be the fastest devices. So if you were to kind of observe this from the perspective of a fast device versus a slow device, over the course of, say, an entire syncing of a transaction group, this is kind of what you would observe. You'd see that the slow device kind of takes a while. It gets a bunch of outstanding IOs. And over the entire course, it's still working on them, churning on them, until we eventually complete, which that means that this is how long it's going to take for us to sync out that data, because we're going to be based off whatever the slowest device or the one that takes the longest to write out. He's going to be the limiting factor. Versus our fast device gets about the same amount of data, and he can churn through it much faster and eventually finds himself completely idle for the majority of that transaction group. Not a place we want to be.
So we can also say that this is a typical case where adding more VDEVs is not necessarily giving us more performance.
So the comment is that
I'm just going to give you a microphone. It's going to be easier.
Can we say that adding more VDEVs is not necessarily giving us more bandwidth in this type of configuration?
Because there's a kind of I don't know, kind of common knowledge that if you add the number of parallel VDEVs, you add parallelism. But here we have something that behaves more like a RAID Z, which is the slowest one has to finish for the transaction to finish. I know it's not RAID Z, but I mean it's the pattern.
Add a little bit, but it's certainly not a linear growth.
Yeah, we would like for it to give us the bandwidth and we would like to believe that, yes, adding devices gives us more bandwidth. And in practice, if you add them at, when the pool is relatively empty and your devices are have about the same amount of allocated space, you will see that performance gain. The problem is that most people don't look at adding space to their pool until they're out of space, right? I mean, we try to get our customers to think about like not what you have today, but what you're going to have, 3 years from now. And I'm not very good at it. And I can tell you our customers aren't very good at it. And if, for those of you, that are in the storage industry, what you'll find is that customers tend to put a little bit on there, try it out, and then if they really like it, then they throw a bunch more crap on it. More than they probably anticipated. They might have told you, yes, I only need 5 terabytes. Sure, give me 5 terabytes. That's all I'll ever need. Until they like your product. Then the next thing you'll realize is that they have 30 terabytes on there, and you're like, okay, that's not what we planned for, and I now have 5 terabytes that are of devices that are totally full, and 25 terabytes that are completely empty. But every single time you try to write, I'm having to do even allocations across that. And that's exactly what we have in this pool. This is an internal system for ours, which happens to be a way that we deploy a bunch of development boxes. Well, it was great when Matt and I first started because, we had tons of free space, one of the few first developers, but of course we hired more people, which meant we needed more space. Maybe I should have had like a timeline of like the number of engineers we hired, but every single time we hired more engineers meant we deployed more virtual machines, which were coming and being served off the system. And over time, everybody started to complain. Yes?
If my disks are from a storage array, does that mean it's better for me to grow them evenly rather than adding new LANs?
So, great question. Growing an individual device is actually an improvement to a degree. Now, every single time you grow one of these devices, we actually create more of the 200 metaslabs. So now you went from 200, maybe you go to 300. You do this enough times, eventually you may have that you find that you have thousands of regions that are all equally sized. So when you get to a point where you're running low on space, now you have thousands of metaslabs that you're going to be looking at, trying to load and unload to see if you actually have free space. So you get kind of some initial performance gains, but you may find that in the long run, you may be suffering just as you would with this implementation. And to be honest, we actually, before we had solutions here, that was our recommendation for customers is grow your LUNs rather than expand. Because at least when we're doing even allocations, as we saw the way the algorithm worked, if we do even allocations and you expand all your LUNs evenly, then you're fine. Everybody just got more free space. But there's limitations on how far you can actually expand, which led people to add. Yes.
Yeah, so if I change one VDEV with, 1 terabyte one, okay, it will resilver, right? It won't keep the fragmentation, right?
So if you actually replace, so let's say, for example, we decide to replace
each one by one.
One by one, we're going to replace each one of these with a 1 terabyte to bring them to the exact same size.
Exactly.
So that's another possible solution, because then as soon as the resilvering completes and I remove the old, smaller device, I get that space. It's kind of going back to the expansion logic once again. So you're just doing it there in like a physical, versus doing it through some storage array that has the ability to expand it based on the LUNs. But it's very similar concept, and it would do the same thing. As far as fragmentation is concerned, your fragmentation number would go down because you now have a bunch of free space that is completely unfragmented. So, but you haven't changed anything about the existing data that's already on there. Mm-hmm. That's still fragmented in the exact same way.
Oh, okay.
George, what about reducing the size of the metaslab allocator? How much free space it's required to look for across the VDEVs?
So it's something that we haven't actually looked at to see if how much of a performance gain you would get. So I think by default it's
10 mega. I think
I want to say it's like 512K per like leaf device. So it depends on if you have like a RAID Z, then that number becomes much larger versus if you just have a simple disk, then it like switches every 512K. We did not do that investigation, but it's possible that might give you a little bit of gain. But now you could round robin much faster through. You're still having to pay the penalty of looking for whatever that small amount is. And now for devices that are free, because it's kind of like a global, devices that have free space now are getting just a trickle. So you may find yourself that performance might actually dive down simply because now we're spending more time just kind of cycling through all the devices, looking, allocating a little bit of space here, a little bit of space here, which we still might have trouble finding. But it could be an interesting thing to investigate.
I think all these are like great ideas of little tweaks, but they don't really address the key problem that you're talking about, which is like some disks are faster than others, and we're allocating the same number to each of them. So we have to wait for the slowest disk to do its, we allocate 1/15 of the data to each of these disks. So we have to wait for the slowest one to do its 1/15 of the amount of work.
Essentially a single-threaded allocator at that point.
Yeah.
Is this cycle of looking on the disks, loading the metaslab to find free space, is this cached in the Arc, or every time it has to do it, it has to do physical, IOs to the disk to retrieve that information?
Yeah. So if the metaslab is already loaded, then everything is just a cache, lookup
in the Arc.
It's actually it's data that's actually not in the Arc, but it's got its own kind of cache. But still, you're able to look through because it's just an AVL tree. So you're able to walk through trying to find individual size regions. That is actually pretty fast. Where it takes a hit is because every single time you load a metaslab today, if you don't allocate from it, you're going to unload it. Which means the next time you come around to it, you may be looking at the exact same metaslab, asking a very similar question you did just a few. We have a tunable now, but you may be asking a very similar question of can I allocate from this metaslab?
Can't we have a cache that holds more of this?
Yeah. So there's now a way for you to keep some of that data for much, much longer, because anticipating that you're going to ask a very similar question, and also the way we select those metaslabs is very different based on the changes that the graph that I showed. That has changed the way that the algorithm works today. But for this, that doesn't help us. So I heard several things. What do you guys think of, how would you try to tackle this problem? If we wanted to come up with a proposed solution of getting bandwidth, dealing with these devices that are imbalanced. So an idea of a VDEV queue for top-level VDEVs. So a weight based on usage.
So I think you're talking about allocate different amounts to different devices based on how much.
Yeah.
How much usage by the free space.
Yeah. So divide by free space. Figure out can I actually allocate more from one and less from another.
Maybe we can store in some way the speed at which the device is responding.
So maybe a way to store how fast devices actually respond, and use that as a way to select devices. All, great ideas. We'll talk about how we address this, and you'll see that they actually, what you guys are hitting on, can actually be solved in a slight variation of the product. So one of the goals is we really think that we should allocate less from these devices because they're mostly full, right? And if we allocate less from them, then we're not spending and using, cycles doing that. And so then that means that we're going to allocate more from these devices to have more free space. But really what we care about is how do we ensure that we utilize all the available bandwidth? Because we don't really care as long as these guys are busy, then we know that we're taking full advantage of whatever hardware and devices you've given us. And as long as these guys stay busy, and we keep them both busy for the entire duration of the transaction sync time, then we can solve this problem. And we can actually solve it by kind of measuring how long it takes for these devices to do allocations. So that leads us to what we're introducing now, which is the allocation throttle. So the way that the allocation throttle works is, and again, I'll talk a little bit about how ZFS does things today and how this differs. So today, when you go through and do all your allocations, you end up getting this onslaught of IOs that get created. So every time you sync out a transaction group, we create thousands of IOs. And they just get thrown into the system, and they get handled by a bunch of task queues. These task queues will actually create like this big fan out. So we start off with an ordered type of write, where we're writing, from a particular file, the first block, the next block, so forth, kind of writing it out. But because we hand these out to task queues, we end up actually kind of mixing them up in order. And the whole reason that we do that is we want to make sure that they go through the compression cycle as fast as possible and with as much parallelism. So we issue these IOs, we issue them asynchronously, and we let them go through the compression cycle. So what we do now is instead, we actually take all these IOs and we throw them into an allocation queue. We then have this global resource that you must get an allocation slot from before you're actually able to go into the allocator. So all these IOs are now coming to the system. They're going to get throttled down here. As soon as you find an available slot, you're granted an available slot. We have multiple threads, so we're actually granting multiple slots at the same time. They're now going to come in and select a top-level device. Now, people familiar with top-level VDEVs? The concept? Top-level VDEV is if you do like a zpool status, is the first device you see under root. So typically on a pool system, you'll see, root, and then you may see mirror, you may see RAID-Z, you may see a disk. But that's your top-level device. That's where we make allocation decisions, is based off top-level devices. So in this scenario, we have 4 top-level VDEVs. We have a bunch of IOs that are going to come in. They've been granted a slot. They're now going to determine which device they're going to allocate from. This is still going to be done in a round-robin fashion. So when we start off, we may start off with a certain amount of work because we only have a limited number of slots. Every device will be given the same amount of work as a starting point. That kind of keeps us in a point where we get all the devices busy right off the bat. Each device now has an allocation queue. You can think of this as like the queue depth if you're familiar with the SCSI world. They each maintain one of these. Those allocation devices get turned into children IOs, which are actually going to go out to the physical disks. So if this is a RAID-Z, there may be multiple child IOs that are actually writing to the physical disks behind it. In this case, this is depicting a mirror where we have one top-level IO gets turned into 2 child IOs. They're going to do the work on behalf of this allocating IO. So once the IO has been issued to disk, we then look at what happens during completion. So now that the device is actually completed, we convert the child IOs back to an allocating IO because that's how we track it. So we find out which top-level IO actually completed work, decrement his individual queue, and give back our reservation slot. Once we've given back the reservation slot, we then simply go back and say, is there any more work to be done from the allocation queue? And the cycle starts over. So what does that mean? We gave everybody, let's assume, 50 units of work. Everybody starts off busy right off the bat. These 2 devices happen to be fast. So they're going to complete much faster. This goes back to trying to keep some kind of telemetry of how fast these devices are. So if we had the telemetry, then we could just make our decision. But instead, we're going to rely simply on the completion of the IOs. As the device is complete, that tells us that they actually are faster. We simply give them more work. So if everybody started off with 50 units of work, these guys can only handle 50 units of work for the entire TXG. The rest of the work would come here. As soon as they complete, they just simply get another device or another allocation. We go back out to disk, keep repeating the cycle until we drain the entire allocation queue. Any questions?
Yes. This might lead to a faster fill rate for certain devices.
Absolutely.
So it might even amplify the imbalance characteristics of the pool.
So it's quite possible that this could lead to a scenario where your blocks that you want to read from might live on one device more so than another.
Yes.
Yes, that's very possible. And one of the things that we rely on very heavily within ZFS is caching. So we're kind of trying to mitigate the right performance by providing enough caching and enough intelligent prefetching to deal with the cases where you may have to go back out and read from fewer devices than you would if you did even allocations. Now, if you have a workload or you run in a scenario where your cache hit ratio is effectively nothing, everything's a cache miss, then there's a way to turn this allocation throttle off.
Well, I mean, I would say, in the common scenario, this is actually going to improve that imbalance of reads. Because, if you look at what we were doing before, we had, a bunch of disks were more full and some were less full. So reads, if we're reading from somewhere random, they're going to go more to those more full disks and less to the less full disks. But with this algorithm, we're going to end up writing more to the less full disks because the less full ones are faster, right? Because we don't have to write as scattered. So this is going to tend to actually more quickly even out the space allocation between the disks kind of implicitly rather than explicitly.
Yeah. I think it may be one could, I don't know if you would do this, but one could envision leveraging this to have these as flash devices and these as spinning disk, right? Even though they may have started completely empty, right? Because if these are faster, then they may receive more allocation over the period of time and become full much faster, which means reads are going to be targeting these devices, but in fact, they are the faster devices to begin with.
Yes, but afterwards,
they'll become slow.
They'll become slow as they fill up, and then so. I think what your concern is: is my read bandwidth going to leverage all four devices
exactly
as a result of this? It's quite possible that it doesn't, but that doesn't necessarily mean that your performance is going to be less.
Because this is basically we're optimizing the write. We're optimizing it for being able to write to all disks at the same time. All disks we're keeping all the disks busy while writing. If reads are basically have the same performance characteristics as writes, then reads would also keep all disks busy at the same time, right? If you wrote a file and it was, 60% here and 60% here and 40% here, then that means we can write these ones faster than these. So then when we come to read it, it's going to read these more than these, but we can probably read these faster than these because we can write to them faster, right? If reading and writing are correlated in terms of their performance.
Yeah, I mean, we made this tunable so you can actually play with it and turn it off.
of course, but okay. How many allocation slots are there?
So the number of allocation slots are based off of the maximum number of queue depths that you allow per VDEV, which I think by default is 10, which is a max.
It's max pending.
It's no longer VDEV max pending. It's like ZFS VDEV async max write.
Yeah. It
write
used to be max pending.
Yes, it used to be max pending, but it's based off of that. So it's a percentage. So you can actually say, I only want it, I want to start off with, if that's 10, I want to have 100, 100 per each of my top levels. So in this case, 400 slots that I can go out, each one of them doing 100 units of work at a given time. But that's tunable also. You can say, I don't care, make it 1,000. And in which case you may not see much queuing happening here at all because they can always handle more work. Other questions?
Is the decision made by the throttle exposed in a case stat or in a way? Because let's say I have a system with many SSDs, like 40 mirrors. So I have 20 top level mirrors. what we see sometimes is that SSD performance will degrade slowly over time. And for now, we rely on IOStat busy output to detect that the SSD is going slow, and we have a threshold where we say, okay, this is bad, and we must change it. With this system, if I understand correctly, we will see it will get less I/O, so the percent busy will be more or less the same as the others. So I won't see it. So I'm wondering if there's a K-stat or a way to get that information.
Yeah, so we don't actually have like a case stat that exposes, each individual devices, like how many units of allocation they got for that transaction group. Definitely you can expose it through dtrace, which is something that we do. And you'll see this behavior in IOStat. Or like if you watch zpool IOStat, you'll be able to see like how much more certain devices are getting, how many more allocations they're getting versus others. And this is the same pool with the feature enabled. Yes.
But I would like to bounce on what the person there said. You said you could have two VDEVs made of SSDs and let's say two VDEVs made of slower disks, but then, if my understanding is correct, you get those SSDs full to 100% fairly quickly when the other drives will be much less full. And so I understand the re-evening out when there's an imbalance, but if that imbalance is intrinsic to the performance of the device, then you just do that. You fill completely the SSDs, and then all you're left is with free space on the slower devices, right?
Correct. Yeah. So if you configured your pool in such a way where you had this big imbalance on performance of individual devices, you would see devices that perform much faster, fill up much quicker.
Or like mirrors versus RAID Z. If you have like two RAID Zs and two mirrors in the same system, you could have better performance from the mirrors.
You may have a similar thing there as well. Right. Okay. Yeah, that's why it's gonna depend. I don't know of too many people that have created that configuration.
No, but you suggested it, so I thought there was like maybe this had some benefit.
I suggested it because that's a scenario where that's very possible, and somebody may actually think of that as an advantage some way. I don't claim to know
what might happen. What might happen is you put 3 terabyte drives, and 3 years later you put other drives, and now those drives have gotten faster. Now you have that intrinsic imbalance because of device performance, not because you have done something as crazy as mixing VDEVs made of SSDs and physical drives, but because of generation difference that have different performance profiles.
Yeah, definitely that's possible. Where as devices
would that create problems with the new allocation throttle? Like some VDEVs get to 100% full, which sounds scary, and then you're
going to see it tapering off. So as a device actually becomes more and more full, it's intrinsically going to slow down.
Okay.
So you're going to see if you have devices that are, extremely fast. I would imagine in the case of like actual spinning disks, you're going to see maybe a marginal difference between generations. But let's take the SSD case. What the expectation is, SSDs would fill up and could fill up much faster. You're still doing allocations to the spinning disk. So you're getting allocations starting off. And this is where having that tunable, determining how many allocations I want to give off, like for the entire system at any go, might be relevant because you can say, I want 500 units of work to go across every single device. That might keep things it won't create as big of a disparity. So you may still be growing both devices at a relatively even rate. But let's say you say something like 100 and you allow SSDs to start filling up. They're going to reach a point where they're not going to be performing the way they did when they were empty. So the devices now that remain for write performance, they're going to start creeping up, and you're going to start seeing a switch in the amount of allocations going from one area to another.
I suppose we'll probably see that between the 6 gig and 12 gig SAS, or
very possible.
Between hard drives. I mean, the hard drive, luckily we've got a couple of hard drive manufacturers here who will be doing a talk later on about these things, but something maybe to keep in mind.
Question over here. You have a mic?
since we're doing that with smaller chunks, isn't there a risk of bigger fragmentation rate?
So the chunk size itself isn't changing.
Okay.
Yeah. So the chunk size still remains 512, and that algorithm still is the same. The only difference now is which device is actually going to be serving more IOs. So you're still chunking them up as they come across. You're still chunking them up in the same way. You're just now doing the distribution slightly differently. And so, any more questions? So this is that same pool that we saw earlier, taking over same sample. So we're going to look at 6 seconds worth of zpool IOstat now with the behavior enabled. And so what we see here is we start seeing devices that are actually doing more work. These devices happen to be some of the faster devices on the system. Devices that are more full are doing less work, but we're keeping them busy throughout the entire time frame of the transaction group. So we didn't stop allocating from devices that were mostly full. We're giving them as much work as they can take. And this is kind of a comparison. So there's quite a bit of data here. So the top devices are the slower devices. Bottom devices are the faster devices. That's what we saw from the previous zpool IOstat. Left graphs are showing you average latencies for doing the complete allocation and write for that device. The right graphs are showing you how much data was written and allocated to that device. So as we see here, we look at these, they tend to be averaging about 80 milliseconds to do an allocation and a write. As a result, they're getting somewhere around 10 meg over that course, 10 megasecond over the course of that SPA sync. The faster devices, which are averaging about maybe 15 milliseconds, are doing somewhere around 25 megabytes per second across the course of that transaction group. Now, if you kind of project out and expect these devices to eventually start to fill up because they're getting that much more data per transaction group, they will eventually start looking more like this. And eventually, the entire system starts to even out. But the advantage here is that I can safely go in and add 2 brand new devices and still be able to keep all my devices busy. So now we can look at all the performance problems that we've uncovered with this particular pool and this type of characterization of problems, and we can say that we have solutions across the board.
What's the overall performance improvement of doing this on the system?
So it's actually quite significant for what we saw on our system. We've seen performance in kind of two different ways. One is we've actually been able to drive this pool. You saw it at like 71%. We've actually driven this pool up to 87% without people complaining, which is very rare for our engineers. Because they're very quick to complain when performance problems get to that point. But I don't have like a specific number, but I think that we're at least like 20% faster in most, like over a time period of a SPA sync, and in some cases more. And we see kind of a variation because it depends on like which device actually starts the allocation. So because you have a round robin type of scenario, so you may end up where you start allocating from, say, the emptier devices first, which means that by the time you get to the slower devices, you've already processed quite a bit, but it depends on that. I don't know if you the VDEV Q stats I know showed a huge improvement from what we saw before.
I know we saw huge improvements. I wondered if you had
Yeah.
any numbers.
Yeah, I know our performance and experience with this has been probably, I would say more positive than we first imagined.
So I think we need to do like a within one day, turn it on and turn it off, and see like the problem is like the way we want to measure it is like you want to measure it in terms of like how many IOPS can you sustain, and this is a production system, so we don't want to just like throw an unlimited number of IOPS and see how many it can take before performance sucks. So what we have is like how many IOPS is it happening to get, but it depends on the load. The load is very variable. And then, also there's like, if you look at it over several days, the amount of free space could be very variable. So, we kind of see like, oh, gee, it's like 90% full and people aren't freaking out. So that's like, we've never seen that before. This is great. But we don't have like really hard numbers on like, you can do X IOPS at Y% full with versus without this change, which would be great to get on like a synthetic system.
Yeah, and I think that part of the problem with like, in the main reason we kind of tackled this particular system was just because of the fact that it already was an aged pool that had gone through several iterations. I mean, we had probably 4 different times where we added devices to that pool. Versus if we just kind of created a lab configuration where we fill one device up, I can't get the same fragmentation on that device, at least and feel like I'm reaching the actual problem at hand. This system was actually great for that because we were able to observe it in a problem state to devise a solution out of it. Yes?
What's the best way to create fragmentation? I mean, if you want to evaluate these kinds of solutions, how would you prepare some artificially fragmented tools?
Yeah, so what's the best way to create fragmentation to kind of like try to look at some of these systems? So we have kind of the worst case scenario that we look at, which is what we call the frag benchmark. And then there's actually something that Matt has put together, which is also very... Even worse. Yeah, it's even worse case, but it's based off customer data. So it leverages the fact that we were able to kind of like get a histogram of how many blocks were compressed or like what the compression ratios were across a pool, and then try to write a data set or a series of data to a pool that kind of matches that same kind of histogram of compression ratios. And then from there, start churning that data. That's probably what I would recommend. I don't know, like, do you... I was going to say, we could probably just make that program available. I don't know if the frag benchmark was ever publicized. That was done by a previous engineer.
I mean, the general story is like, basically we just like create a couple of big files with like 8K record size and do random writes to them. And then wait until the like initially performance is going to be good, and then performance gets worse and worse and worse. And then we just wait until performance doesn't get any worse, and then that's as bad as it gets. And then the variables here are like, how much of the pool do you fill up? Like, are you saying the pool is going to be 90% full versus 50% full? And then like the block size, and then the distribution of compression ratios. So like most of these tests that you showed were with just like a constant, with no compression, where it's just like all 8K blocks. And then we also have done tests where we make each block get compressed a different amount. So you have all these different physical block sizes that we're trying to allocate, which is like really, really horrible for compression. You can end up getting like tons of gang blocks and like other like really horrible things happen, which is very interesting.
Might I suggest using VTbench for that?
Yeah, and so like the other benchmark, our frag benchmark, as Matt kind of mentioned, it uses FIO. So again, creating, you figure out like you want your pool to be 60% full, create a file that consumes 60% of the space, and then it runs FIO kind of like over top of it using random writes. And then you kind of monitor the throughput, look for a steady state, and that's when you know that you've kind of reached that threshold. That's a good way to attack it. Don't go away just yet. there's actually more. Which I don't have a lot of slides on this, but I know Matt mentioned this. But we did want to kind of announce compressed arc, which is actually functional and in our internal repo, and that has been completed. As Matt kind of mentioned earlier, compressed arc effectively mimics what the compression that you're using on disk. So if you're using gzip9 on disk, you effectively have a gzip9 compressed version of the block in memory. Just some preliminary tests that we did. I had a small system, 20 gig of arc, created a 35 gig file on using LZ4 compressed file system. I'm getting about 2.64x compression ratio for that file. I'm actually able to read that entire file into the ARC and keep it completely cached. So all subsequent reads come directly from the ARC, even though it's 15 gig larger than the existing ARC. This has been integrated also with L2ARC, so L2ARC behaves a little bit differently. So I'm interested to see how persistent L2ARC is going to...
it's going to be a race to the gate.
Yes.
See who has to do the integration work.
So there's a lot of merge changes potentially coming, but we're getting this kind of finalized. This is going to be in an upcoming release of ours, and then as soon as we get it completely, polished for upstreaming, we'll get that out there. Just like the other pieces, there are switches to turn compressed arc off, so people can try it out and see what they think. But this is a new thing that we're excited about, and wanted to announce it to this group. Yeah, so this is probably like fall time frame is what you'll see from Delphix coming upstream is about that.
Is it per dataset tunable?
So turning it on and off is like there's a big switch which turns compression arc all the way on and off. If you want to try it on a per dataset basis, then it's going to be based off the compression ratio or the compression algorithm you use for that dataset. So if everything is uncompressed except one, then you would only have those blocks that would be uncompressed or compressed in the arc.
I could see that as a bit of a problem potentially. What if you have a pool that has a mixture of some real-time decompressible stuff, LZ4 compressed? Obviously, you would want to keep that compressed in memory because it's cheap to decompress. But what if at the same time you also have some stuff in there that's gzip or maybe some future archival algorithm we come up with, and for performance reasons you would want to keep that uncompressed in memory, compressed on disk. So essentially your workload would rely on memory access being fast.
Yeah, so today that is not possible. And depending on your workload, so if your workload is one where you're going to be accessing that frequently, then for frequent accesses, things will stay uncompressed. But if it's one of those where you're accessing it once and you want that initial access to be fast, and then you're going to wait, hours before you access it again or days, and you want that access to be fast, then that isn't possible today.
George.
Yes.
So you read the compressed block and store it in memory.
Correct.
It's not recompressed. Just
Correct.
to get it absolutely clear.
Yes.
Okay.
Yeah. So whatever form the block is on disk is the form that it will take in memory. The advantage that this gives us is, as Matt also mentioned, is compressed send now becomes simpler because you already have the compressed block in memory. We actually have a design for a compressed send receive that allows us to send this compressed block from memory without decompressing it at all and writing it in a compressed fashion all the way to disk.
I don't know if it's in the current version or in a future version, but I saw something on a slide about metadata being LZ4 compressed. So does that apply to cached metadata?
It would apply to cached metadata
Currently,
as well.
it's not, right? Metadata is read,
I think it's
uncompressed, and stored in ARC uncompressed.
Yeah, so today, everything in the ARC is uncompressed.
Okay.
Moving forward, even metadata, which is currently LZJB, is it now LZ4 by default? So LZ4 metadata would stay compressed in the ARC, and then uncompressed whenever you access it.
Unless the big switch is turned off.
Unless the big switch is turned off, or it's data that's like accessed, repeatedly.
Okay.
Cool.
Thanks, everyone. I have another question. Yeah, sorry. There used to be something, kind of a blog post that had to do with some tests doing on Nexenta. Basically, it was too much RAM is too much RAM kind of thing. Like if you really put too much RAM in a system, the L2R reclaim thread would take forever or something like that. Is that still the case? Do we have to be scared about putting a lot of RAMs into systems?
I think that I don't know the blog post, so I'm not sure if exactly this is it. I'm wondering if it was referring to the fact that when you had very large L2 ARC devices, that the amount of memory consumed to actually store the pointers to that L2 ARC was actually pretty high, which has changed. So I don't know if that's what they were referencing.
I think it was more simply that above 224 gigabyte of ARC, there was a problem of really the ARC reclaim taking too much time.
Yeah, the KMM read issue.
Oh, yeah, that's
shall not be talked about.
Yeah, so that's slightly different.
That's kind of a different issue. I did some work that was integrated at the end of last year that makes that like slightly better, in that it won't need to KMM reap as often, but the real solution to that is kind of a bigger project that I'm also working on, that's related to some work that's happening on Linux, where we will be able to like rather than having different KMM caches for like 128K blocks and 16K blocks and 8K blocks, and then having to like shrink the ARC and change which ones are being used, we would be able to compose a 128K block in memory from a bunch of 4K pages. And then when you are shrinking the ARC, you're just freeing those pages and you aren't involving KMM at all. That's like, I have a prototype of it. It needs some more work.
But currently, what is safe? If we want as much RAM as possible because we want a big ARC to store metadata and all kinds of things.
It depends a lot on the workload.
Yeah. What's the workload?
Well, it's a varied workload. I don't have a single answer to that. But the thing is there a number that it's safe to have, and above that we may run into this problem? Is it 256 gigs? Is it 512 gigs? What?
I mean, you guys have a lot of varied workloads as well, and you're saying 256-ish?
Well,
is that right?
I rarely hear of a system that has more than 512. And I think, that's sort of the general recommendation. I mean, don't quote me on this. So this is sort of going by what I remember off the top of my head, but the general consensus is somewhere between 256 and 512 is sort of a sweet spot. Yeah. Above that, you might run into some issues. But I've seen systems hurt even below that. But it really depends on your workload. Yeah, the amount of ARC turnover you have.
We've done a bunch of more work too to mitigate this in terms of like the KMM reclaim can end up like using all CPU, and then like your network connections drop and whatnot. We've done some work to mitigate that, so that might mean that you can bump it up higher.
But if I have to make a purchase decision today for a big pool, a petabyte pool, I want to get as much memory as I can, right? I can't go with a terabyte of memory because you're telling me that I'm going to hit this problem if I have too much RAM, therefore too much ARC, right?
Yeah, I mean, I think I think your mileage will vary based on workload. So it might be that 1 terabyte for your case might be fine, but we've definitely seen issues as you go above and beyond 512 gig. At least on Illumos, there's things that need to be addressed. We've seen, I think our largest customers are running like 384. I think we may even have some that are at 512, but that seems to be kind of where there's still some work to be done. We've already gotten quite a bit of the changes that we want to do as far as KMM Reap itself is concerned in place. Now we're looking at taking KMM Reap completely out of the picture, at least on Illumos, and I'm sure that...
Just to clarify, like everything that we've been talking about here of like this, your question, is all specific to Illumos.
Yeah, because
So we're assuming that you're talking about Illumos, but I think you're not. You're talking about FreeBSD, which I don't think that any of us have like the three of us
I
don't
thought
have
it
any
was
experience
general
with.
to ZFS, whatever
It's
the
not.
platform is not.
It's
Okay.
definitely
So,
not.
so if I'm on FreeBSD, I can put a terabyte of RAM and I can have 800 gigs of ARC.
We don't
ask
know.
the FreeBSD guys.
Yeah,
well, without
we
jumping
don't know.
in, Solaris, well, Oracle Solaris is the ZS3 appliances have up to 3 terabytes of RAM.
Yeah, they've obviously
So
done some work in this
they've done
area.
some work to improve that anyway. So it's we know it's possible. You know,
It's
to get up to that.
definitely platform. This
It's
this
definitely
question is
platform
dealing with
specific, yeah.
not. This is not really a ZFS question. It's a platform memory usage question, and sorry, we kind of started answering it based on our experience with the Lumos, which is not really.
But thank you for
what you're
clarifying, because
asking.
I was
Yeah,
not aware
sorry.
that it was a Lumos based.
Yeah,
And if you have to provision systems and make purchase decision, how much RAM is a big question on the table for every system you build.
The work that Matt alluded to, that he's got a prototype that would be more ZFS specific and presumably one that would carry over to FreeBSD. Yeah. But and primarily the reason that a lot of that work is being done is because KMM on various platforms behaves very differently and inevitably probably has problems at different points. We don't know what FreeBSD might be. We're definitely happy to tell you all about Illumos' problems.
Another little one. A couple of years ago, OpenZFS Day 2013, maybe 2012, but I think it was 13. I think it was you. You ended the talk with a very enigmatic. I was on the live stream that day. On 4K discs, really, you shouldn't do RAID Z. Is that still a concern? Is that still a valid thing?
Depending on the workload. So, can you bring it by blog post? I wrote a blog post which is directly addresses this issue. The issue is essentially like if you're using 4K discs with RAID Z, and you're using small record size, like 4K or 8K record size, you're probably shooting yourself in the foot. Like if you're using 4K or 8K record size, don't use RAID Z regardless of if it's 4K or not.
But 4K record size, usually on a normal workflow, you may have all kinds of record size. You're not necessarily blocking it at 4K.
Like the default would be 128K record size, and so this is the blog post that I'm talking about. I have this great graph. But this is talking about kind of like the additional space overhead based on sector size and all this. We can get into the details offline, but in general, like if you're using 4K devices with RAID Z and you're doing general purpose use with the default of 128K block size, it's going to be fine. It's only these specific small record size uses, because most of the time, even if you're using 128K, if you're using the default of 128K record size, only small files are going to go on these smaller blocks. And almost all the time, most of the space is in big files. Even if you have a million small files, it's usually going to be those 100 big files that are actually consuming most of the space, and those are using the 128K block size. I mean, most files, like 128K is tiny nowadays, right? Like even a picture file is like 128K blocks, or like 128K blocks. So
no, we don't, because what we do is we do NAS that serve files over Samba, over SMB and AFP to Mac and Windows clients. And so we have, photographers have big pictures, but also maybe a lot of Word documents that are smaller or small
You
things.
should
So
be fine with that.
it's a varied block size.
Yeah, I wouldn't worry about that.
Okay,
that use
so we
case.
can use. Okay.
Yeah, you should
and,
be
and
fine
what you're
with
saying
RAID
applies
Z.
to RAID Z or RAID Z2 or RAID Z3.
All of the
RAID
RAID
Z.
Zs.
Maybe show the other graph. That shows it better.
Which one?
And the new feed.
You show a RAID Z stripe, not in this one. You gotta go back to the blog post.
Oh.
There's a feature now. Is it a current or future feature that there's larger block size, like up to 1 meg, or how much?
Up to 1 meg or more.
Is that implemented now?
Yeah, that's in.
Okay. And is it by default?
No, the default is still
you have to
128K.
activate it.
You would have to increase the record size.
Is there what is the benefit penalty of activating?
It was primarily motivated not to change the default in a sense of do no harm.
Yeah.
we don't want to change performance characteristics of workloads that depend on this.
But if I activate it, what do I gain? What do I lose?
So you're going to gain performance, especially on large files that are sequentially accessed, like video files, for example. Especially on RAID Z, even more so. But even on Mirror, the really killer use case for this is video serving, where you have like a lot of video files, and each one you're serving up a lot of streams at the same time. So it kind of looks like random access, but you can afford to cache quite a bit of it. So rather than like random access of 128K, you're doing random access of 1 meg or more. And so you're able to get much more megabytes per second by doing it in 1 meg chunks than in 128K chunks.
But small files can still allocate a small block, right?
Yeah, yeah. Sure.
So there's no penalty. There's a potential benefit.
The penalty would only be that those 1 meg reads and writes can kind of stop up the pipeline, right? Like if you're using a disk, then a 1 meg read is going to take longer than a 128K read. So if you have other latency sensitive operations, then the latency is going to go up.
Say, for instance, that you have a workload, a data set which you've not previously tuned to a specific record size. So your workload kind of assumed 128K. If you do a smaller write to it, not a full block, right? Where you have some sort of workload that does partial writes to the blocks. What we do in memory is we do a read, modify, write. So we read the block off the disk, modify that, and then write a new copy. If all of a sudden you have to read a 1 meg chunk rather than 128K, your read, modify, write overhead just octupled.
Yeah. Okay. But hopefully you aren't doing those. Like if you're using 128K record size, hopefully you're just like reading files sequentially and writing them sequentially. Typically, that's
so. Is there a rule of thumb? Activate only in case of this workflow, or you just have to test for each workflow and decide if you turn it on or off?
I would suggest you test based on your workload to see.
Yeah.
Because the modification penalty could be extremely huge for you, especially if you're having, if people are changing a very small portion of the file.
Yeah. Like you mentioned these Photoshop files where they're modifying just a portion of the file, the record size would have a big impact in that scenario.
Or say you're running a database.
Running a database, you probably have already turned it down to 8K or 16K.
I'm talking about
but yeah.
a sysadmin who didn't.
Yeah.
Is it a per pool setting or per ZFS?
Per file system.
Per file system. Okay. Thank you.
And then we'll probably also, have a conversation from either HGST or Toshiba about, availability of like 4K drives, 512 and 512 native, 512 emulated.
4K is old. I've seen
how
8K SSDs.
And how that all comes in. So that'll be this afternoon, right? From both HGST and Toshiba. So yes, from a hardware perspective. But any more questions for George?
Thank you.
Okay, thanks very much.